So, let us look at another example, but before that let me also introduce a further generalized scenario of variable endpoint criteria, right. So, I am going to talk about a topic that is known as the transversality condition. So, what exactly is this condition and when is it going to be applicable? The transversality condition. Okay. So, what exactly is this? So, suppose we consider an extremal which is y of x. So, y of x is an extremal. It joins a point, let us say x naught y naught, to a curve. So, let us say this is a curve which is denoted by gamma. We will show that the joining point is such, this point let us say x1 y1, it joins, the extremal is such that it joins a point to a curve, and the joining point is such that the point of intersection is always at right angles. This is something we will show very soon. So, this question is, what is the condition, what is the equivalent boundary condition for this setup, where we have to extremize a functional, extremize subject to one of the endpoints on a given curve, on a specified curve, right. Or we could also have a case where the extremal y of x with two endpoints x naught y naught and x1 y1 are on two specified case, are on two specified curves gamma 1 and gamma 2, right. Well, we will show that in both these points of intersection, this curve intersects the extremals always at right angles. So, again we would like to figure out what is the criteria, endpoint criteria for this case as well, or in general what happens if the endpoints lie on a specified curve, right. So, what I said is the following. So, consider an extremal y of x, consider an extremal y of x joining a curve to a fixed point, that is my case 1, which is this case, or joining two curves, right, which is this case, right. More often than not, many of these problems will involve, for example, finding the shortest distance between two curves, or the shortest distance between a point and a curve, or a shortest distance between two curves, right. So, for such a case, how to approach such a scenario? So, what we do is, in this situation we are going to specify, we first let the curve be defined in the form of a parameter. So, we specify the curve gamma parametrically, right. So, we are looking at case 1, right, this is my case 2. So, I am talking about case 1 here. So, specify my curve gamma parametrically, right. So, let me call this as the curve with components x gamma of zeta, x gamma of xi, y gamma of xi, right, where my so which means my variation delta x now is, they are all lying on the curve, which is dx d xi, right, this is dx gamma. So, x lies on gamma times delta xi, right, and my variation y is dx gamma, well, dy gamma d xi times delta xi, right. So, I specify the curve parametrically such that delta x is this and delta y is this, such that, so in this case let us look at my endpoint criteria. So, my endpoint criteria condition becomes p delta y minus h delta x at the point x1 is equal to 0, right. So, again this condition is applicable at this particular point x1. Okay. So, this is the condition I am going to talk about. Okay. So, I am going to replace my delta x and delta y since they lie on the curve. So, which means what I get is the following: p times d y gamma d psi minus h times d x gamma d psi times d psi, this is equal to 0. And further notice, further note that x gamma del psi del y gamma del psi, these are all tangents. These are my tangent vector. This is the tangent vector to the curve gamma, right. So, this is nothing but the tangent vector. So, let me call this criteria star. So, my star says that my star says that my tangent to the curve, gamma is perpendicular to the vector v, which is prescribed by minus h comma p. Why? Because notice that this is nothing but the dot product of minus h comma p dot with del x gamma del psi, right, comma del y gamma del psi, right. So, this is the dot product, and we show that the dot product is 0, right. So, now we have shown that the transversality. So, this is indeed, this is what we call as the transversality condition, right. So, what it says is that whenever the endpoints they meet on a curve, they will always do so such that they meet at right angles, right. I call this in short notation TC. Okay. Let us look at a quick example in this class of function. So, we have to find the shortest path, from origin, to the curve r gamma, which is x gamma y gamma, right, with the path length r gamma with the path length given by f of y, which is the integral from 0 to x1, square root of 1 plus y prime square dx, right. Okay. So, what have we got here? We see that of course, the solution to this integral is a straight line. Let me calculate the various quantities. So, the momentum function will be partial f partial y prime, where my f is this quantity integrand. I see that this is y f of y prime divided by square root 1 plus y prime square, and my Hamiltonian is y prime partial f partial y prime minus f. This is after evaluating comes out to be minus 1 by 1 plus y prime square, right. My transversality condition, let us plug in, well, I do not need to solve the Euler-Lagrange because I already know the extremal, which will be a straight line. I need to figure out the family of the specific family of the straight line. So, I am going to directly use the endpoint criteria, which is now going to be the transversality condition, because one of the endpoint lies on the curve, right. So, I use the transversality condition TC, which tells that P del y del gamma del y del psi minus h x gamma del psi, this is at x1 is 0, and we plug in P and H, I see that this is also equal to y prime d y gamma d psi plus H was equal to minus 1 times dx gamma d psi divided by square root 1 plus y prime square. This is equal to 0, right. And this is also, we are also saying that the dot product of x gamma del x psi comma del y gamma del psi dot product with 1 comma y prime, this is equal to 0. Note that this is nothing but the tangent to the extremal, right, the extremal curve that we need to find, and this is nothing but the tangent to the curve on which the endpoint is defined. So, the dot product is 0. So, I know that further equation, the further solution to this equation is possible once we know the exact form of gamma, right. So, let me look at some specific cases. So, suppose I look at a simple case where my gamma is the arc length of a unit circle, arc length of a circle centered at origin, arc length of a circle centered at, so I separate this right up, centered at origin, and then I expect that my extremal y of x will be the radius, right. So, because in that case, for an arc length of a circle, only the radius is going to meet the arc length at a distance at perpendicular to the arc length, right. So, radius starting from the origin, right. So, that is my extremal. So, that can be found directly from the transversality condition. Let us look at a slightly more involved case. So, let me give gamma. Suppose gamma is of the form, gamma of psi is of the form xi minus 1 comma xi square plus half, right. So, my transversality, I know that my extremal y of x is mx plus b. This is directly from Euler-Lagrange solution of geodesic, right. So, we are solving the geodesic problem. From here, what I see is the following: the transversality condition gives me, if we differentiate, I see that this is 1 comma 2 xi. The dot product is with the tangent to the extremal, which is equal to 1 comma y prime, which is m. So, my transversality condition is the following, right. So, from here I see that the condition reduces to this 2 xi m plus 1 is equal to 0, or my xi, the variable xi is negative 1 by 2 m. Okay. Now, further we know that there is a common point of meeting of the curve and the extremal, right. So, at common point of intersection, I see that y at x1 is also equal to gamma at xi evaluated at x1, right. So, what have we got is y at x1 will have the following form. So, what have I got is, so y at x1, the xy coordinates are x1 comma y at x1. Well, certainly the equation, well, we have one more condition that we have. Well, the original problem says that the starting point is from the origin, right. So, my extremal will be such that my b is 0. So, my extremal is y is equal to mx, because only this straight line passes through the origin. So, which means my points y are at x1 is x1 comma m at x1, right. And on the right hand side at x1 I see that this is also equal to zeta xi minus 1 comma xi square plus half, and this is also equal to, note that xi is negative 1 by 2m, right. So, if I plug xi, I get that this is negative 1 by 2m minus 1 comma 1 by 4m square plus half, right. Okay. From here I have two equations and two unknowns for m and x1. I solve, I see that the equation that I get is 4m cube plus 1 is equal to 0. It is a cubic equation, and the only real solution I get is negative 1 by cube root of 4. So, this is the only real solution, right. And then the rest of the solution will follow. Namely, my extremal now is y is equal to mx, which is negative x by cube root of 4, which is my specific class of function which satisfies the transversality condition given the curve, given this curve, right. So, that completes the description of this problem, and let us now look at another, generalize this transversality problem for the class of functional having several dependent variable. So, what I just said is the following. So, problems involving several dependent variables, right. So, we are talking about extremals of this form. Extremals, we are talking about extremals of the form j of q bar is equal to integral from t0 to t1 L of t comma q bar dot dt with endpoint condition given by pk delta qk minus h delta t is equal to 0 with endpoint condition as follows. Okay. So, now further to impose the transversality condition, we also have to impose the curve on which one of these or both of these endpoints lie. So, suppose t, my free variable or independent variable, lies on the surface, because now it is multiple dependent variables. So, we have surface given by t equal to psi of q bar, right. So, t lies on the surface such that t is equal to psi of q bar, which means that so I need to find the variation delta t and delta q bar or delta q1 delta q2. Now, we look at that variation one by one. So, let me just say that we look at variation only in the first component of q, assuming the variation in the second component is absent. What I said is the following. So, consider the variation in only first component, only the first component, let us say q1, right. So, which means we are holding q2 to be constant, the second component as constant, and what I get is, from here I can see that since t is on the surface, right, I see that delta t is delta t is partial psi partial q1 times delta q1, right. So, delta t can be expressed in terms of delta q1 as follows, because t lies on the surface. Similarly, for variable q2 for the other component q2 with q1 fixed, I can derive similar relation between delta t and delta q2. Okay. So that's it. So of course all these extremals are such that they satisfy the system of Euler-Lagrange equation, right. So now notice let me call this as star and call this as double star. So from here star, my fixed endpoint condition P delta x, P delta y minus h delta x condition. So y now is P delta q bar minus h delta t set equal to 0. Condition reduces to this simplification reduces this criteria to P minus h times partial psi partial q1 times delta q1 set equal to 0. Similarly, from the other coordinate I can find, setting from the other situation I can find a similar relation with respect to q2, right, delta q2. So students can complete this expression, which is very much identical to the first one. So let us look at an example in this class of problem, right. Okay. So let us look at an example. The example I have is as follows. I need to extremize j of q bar, which is integral 0 to t1 square root of 1 plus q1 dot square plus q2 dot square dt. I need to extremize this where q bar of 0 is 0 and my t1 is variable, but t1 lies on the surface psi of q bar, which is given by q bar of psi of q bar of t1, which is given by the following curve, which is q1 at t1 minus 1 square plus q2 at t1 minus 1 square under the root. Let me call this curve as A1. So essentially this curve is the surface of a cone. So this particular surface is the surface, students can draw that surface of a cone with vertex 1, 1, 0, 1, 1, 0 in 3D. Okay. So essentially the problem is asking, in the geometric sense the problem is asking, find the curve in R3 from the origin, right. We have taken t equal to 0, right. So from the origin to the cone with minimum arc length, right. Notice that this quantity inside this integral is the arc length functional. So we are trying to minimize the arc length. Okay. Now, well, of course we need to satisfy the Euler-Lagrange. My Euler-Lagrange equation, the system of Euler-Lagrange for this is a geodesic problem. My Euler-Lagrange equation will directly give me the solution as straight lines. So I need not solve that. I see that my solution q bar in terms of t is in terms of these constants alpha bar t plus beta bar, where my alpha bar and beta bar are vectors, because this is a set of two equations, beta 1 comma beta 2, and we see that further we are given one boundary condition, q of 0 is 0. So, which means that since this straight lines passes through origin, right, since this boundary condition, right, since I have q bar at t equal to 0 is 0, I necessarily have that beta is 0, identically 0. So, all I need to do is to find this alpha, alpha 1 and alpha 2. Now, all I do now is, well, we have already utilized all our boundary condition. What is remaining is the transversality condition. So, to find the transversality condition, let us find the momentum and the Hamiltonian. So, my momentum pk in terms of, so this is partial f partial qk dot gives me qk dot divided by square root of 1 plus q1 dot square plus q2 dot square, and my Hamiltonian H is summation qk dot k from 1 to 2 pk minus L, and after simplification I get that this is the expression minus 1 by q1 dot square plus q2 dot square, right. I see that my transversality condition reduces to the following. For q1, so I see that this is the set of transversality condition derived in my previous slide. So, del L del qk dot minus H times del psi del qk is equal to 0, right. So, this is for k equal to 1 and 2, and from here I see that I simplify this expression on the left hand side to get that the equation is qk dot, after plugging in L, H and psi, qk dot plus del psi del qk is equal to 0. I already know the equation of the surface psi, and after plugging in that value I immediately get that alpha k comes out to be minus alpha k T1. So, this is evaluated at t equal to T1, t equal to T1. So, minus alpha k of T1 minus 1 divided by T1. So, from here my simplified expression is 2 alpha k T1 is equal to 1, or so this is satisfied for both k equal to 1 and 2, or this is equivalent to saying that alpha 1 is equal to alpha 2, right. And also the fact that well, let me renumber some equations. I call this as A3, and finally I call the equation of the straight line, I call this equation of the straight line as my A2. So, notice that from A2 and my equation of the surface, my surface equation is A1. So, from A1 and A2, plugging in the values, I come to the point where alpha 1 square plus alpha 2 square is equal to 1, and given the fact that both alphas are equal, I see that alpha 1 is equal to alpha 2 is 1 by square root 2, or my extremal, my q1 is equal to q2 is 1 by square root 2 times t. So, I have found the extremal, and students can check that for this extremal the point of intersection of the curve psi of q bar with the extremal q bar is at point 1/2 comma 1/2 comma square root 2. Okay. This needs to be checked, and I leave it to the students to check, since everything is given to us. So, I end my discussion in this lecture, and in the next lecture we are going to see another formulation of Euler-Lagrange, which is going to cover a broader class of problems, especially arising in continuum mechanics. Namely, we are going to describe the Euler-Lagrange via the Hamiltonian formalism. Thank you for listening. Thank you very much.